Hello everybody, Adam Lusick here, and today I'm going to be highlighting 3 specific AI-related projects that I've put together over the last month or two to make my life a little bit easier. The 3 projects in question that we're going to demonstrate how to use today are going to be PPT to Desk to Start or PowerPoint to Description, which allows you to convert PowerPoint presentations into semantically rich text using vision language models. The second is going to be NeedleInAVidStack, which allows you to extract, timestamp, and analyze specific content from video collections using language model-powered audio and video processing. And then the last but not least third project is QuicKB, which optimizes document retrieval through an end-to-end machine learning pipeline that handles document chunking, synthetic data generation, and embedding model fine-tuning. All 3 of these projects were made out of different issues that I encountered when working with language models and other AI-related systems in both my personal projects and professional endeavors. So I hope to give a good overview of some real practical applications of artificial intelligence that I've seen come up in my day-to-day life. So to kick things off, let's take a look at the first of these 3 projects, PowerPoint to Description. The main pitch of what PPT to Desk is meant to do is really be able to take PowerPoint presentations, a common format that we see across many different enterprise applications, and be able to convert them into something that can be used in more text-based processing systems. The biggest example you might start to think of with something like this is how would you create a retrieval augmented generation system that relies primarily on a database that consists of unstructured PowerPoint presentations. As we know, language models are incredible at processing things that are very text heavy. Things like Word documents, text documents, PDFs, anything like that that contains a lot of very direct and descriptive text, language models already have no issue processing. But in the case of something like a PowerPoint presentation, this becomes a little bit fuzzy. The main reason being is that PowerPoint presentations are meant to be more of a visual way of displaying and telling some sort of data story. Looking at this example of the June 2022 corporate overview from CrowdStrike, we can see that they follow a lot of the best practices when it comes to creating PowerPoint presentations. Less of what you want to do is keep a lot of text on your slides, rather visually show what you're trying to say, and then usually what happens is the rest of the data and information is filled in by whoever's auditorily presenting. And while this format is phenomenal for a human audience because we can very clearly interpret and see what is trying to be displayed and what message is being portrayed visually through things like icons, graphics, tables, and charts, this doesn't translate very well when you go through traditional text scraping methods. Looking at this slide more specifically, we can interpret that what the CrowdStrike team is likely trying to show in this Zero Trust slide is how their intelligence and managed services brings together the workload, different identity identifiers, and data together through their service to do these different protection and security benefits. The issue, however, is while I was able to do this interpretation myself, if we look at something like Unstructured's Document Loader, which is a super powerful scraper for things like PowerPoints and PDFs and whatnot, the same slide comes out to look a little bit like this. So we can see the Zero Trust workload identity data, workload data identity, and a few of the different key points that they have on the slide here. However, through this pure text scraping and flattening, we miss a lot of the good semantic rich information that the slide is trying to portray. This becomes even more egregious in the case of things like charts, which might be some sort of collection of different vectors and images and whatnot. We see this slide convert literally just to a line-breaked list of numbers. Very difficult if you were just to scrape the text from this PowerPoint and run it through a language model for some sort of synthesis and interpretation for it to truly understand what these numbers might represent or how they're related in comparison to something like a slide here. However, one thing that I realized is if you look at some of the latest language models with vision-enabled capabilities, you can see that if you pass in the visual representation of that slide, it's able to actually do a lot of good interpretation. We can see as it's happening right now, GPT-4o take a picture of this slide and be able to do a lot of the good interpretation about the market growth and the market segments and how all of this is being displayed right now in this slide. So taking this idea one step further, what I did is put together PPT to Desk, which essentially is a way to automate the conversion of multiple PowerPoint files all at once through vision language models to do this conversion into text, maintaining the rich semantic information that's being displayed through things like tables and graphics. The main feature of this is really to be able to connect the vision language model to a large collection of PowerPoints, so being able to process through a folder filled with many, not just one at a time. So I put in the features to be able to do this conversion and also support a lot of the current model providers, both through the developer APIs as well as the enterprise-ready cloud environments like GCP, Azure, and AWS. The main pipeline here is going to take your PowerPoint presentations, do a step conversion into PDF format so that we can flatten out the PowerPoints, as it turns out that the back end of PowerPoint and all the XML and Microsoft specific dependencies in there can be a little bit difficult to work with, especially if you're on Mac or Linux based systems or want to do this headless. And then what we do is we take those PDFs, convert each of the presentations into individual slide photos, and then programmatically run them through a vision language model to generate this text representation of the slides. Much of the conversions here are actually going to be ran through LibreOffice, which is a great application that's able to do headless conversions of PowerPoints into things like PDFs, so this will run nicely on Linux-based systems. You don't have to have any of those weird dependencies with Microsoft or Windows. It's all put together as a command line tool too, so you can run this as part of a automated pipeline, cron job, or any sort of those DevOps automation things if you're familiar with them. As a plus, I also have a way to run LibreOffice in Docker, so if you don't want to rely on a local installation of LibreOffice or are using some sort of deployed cloud environment, this is completely an option as well. So after cloning the repo, creating a virtual environment, and installing the requirements, what you can do is just type in docker compose up and start the LibreOffice Docker container. So at this point, we're ready to actually configure the script arguments, which back here in my README, I have quite a bit of, but for the most part, they're pretty self-explanatory. We have an input directory, which is the path to the PowerPoint files, an output directory, which client you're using, whether that's Gemini, Vertex, Anthropic, Azure, AWS, or OpenAI, the specific model that you want to use, any additional instructions that you want to pass along with the default prompt that I have, and then some pointers towards the path to your LibreOffice, whether it's a local installation or running on the port with Docker. I have a few other specifics for things like Vertex, Azure, and AWS if you're using one of the cloud environments, as well as some additional example commands if you want to see some of the ones that I've used in the past. For this demonstration, however, we're going to be using this specific setup. So I have my input directory as ppts, which is this folder here. Within this folder, I have 4 quick example PowerPoints. The output directory is just going to be output in the ppts folder here. We're going to path to our LibreOffice URL. The URL is going to be this localhost one, as I'm currently running it on Docker, as we just launched. We will have the model here be Gemini 1.5 Flash to do the interpretation. I want to save the PDF and the intermediary images that it's going to be creating. I'm also going to pass a few more instructions along with the base prompt. More explicitly, I ask it to describe and interpret the non-text element relationships and what they are portraying on the slide. I have to specify that I'm using Gemini along with Gemini 1.5 Flash, pass in my API key as well as a quick rate limit to make sure that I don't go over my rate limit for my current developer account. With that configured, we can paste that back into our terminal here and run it off. So we'll see that it's immediately going to connect to the LibreOffice Docker image that we have here, call it, convert the PowerPoint into a PDF, and then it's going to start running each of these individual slides through our Gemini model. So I'll be back in a second once all of this is processed. Just a few minutes later, what we have are all of the resources that PPT2Desk has created here. So let's take a look at the main file of the CrowdStrike investor output. Looking for slide 16 from our example slide here. If we just grab that out of the output JSON file and print out what we got, we can see a few things. The first are going to be just a pure output of a lot of the text that's actually on the slide itself. And then what the model is able to do is actually do a little bit more of this interpretation of the main themes and ideas. So we can see that it is identifying the different arrows pointing from different parts on the screen, saying that it suggests things like identity is verified before accessing the workload. And we can see that the overall design use, colors, icons, and text represent the concept of zero trust and workload identity and data protection within the framework of intelligence and managed services. Pretty much exactly what we were able to glean and interpret ourselves from this presentation. So now we have all of the semantically rich text conversion of each one of these slides in a nice JSON format across all of our different PowerPoints here that we can use for any sort of downstream processing task or other language model ingestion. A pretty nifty way of taking one of those super useful formats that we see commonly in our day-to-day lives and being able to convert it into something a lot more usable in AI systems. But with that, we can move on to talk about the second of the three projects we're highlighting today, NeedleInAVidStack. This one is less of a conversion tool and more of something that's actually meant to automate a process. My main pitch for why I think this needs to exist is because extracting and organizing content across vast video libraries is really a time-consuming and manual process. So what this tool aims to do is automate the task of extracting and timestamping out specific content using different AI models. As it turns out, a lot of the state-of-the-art language models are now starting to be incredibly well versed in multimodal inputs and outputs. More specifically, looking at the model cards for something like Gemini 1.5, which we just used the Flash version in our conversion earlier, we can see that it allows the input of up to 2 million tokens, of which can be 7,200 photos, 2 hours of video, or 19 hours of audio. And it's able to understand and process all of these different modalities inherently. More specifically, it's able to understand transcriptions of and refer to timestamps of audio files. So the scenario that this aims to apply that capability towards is, what if you have many videos and you're trying to look for just specific parts that could be common across all of them? But rather than be vague about it, what I'll do is show a specific example. So for my scenario, what I'm going to demonstrate is this specific video library. On Stanford Online's YouTube channel, they have Andrew Ng here, who is, of course, a phenomenal representative of the machine learning space, and he has a couple of these long-form videos interviewing some other prevalent individuals, such as Chelsea Finn, Fei-Fei Li, and Chris Manning, on all sorts of different AI topics. To further the scenario, let's say I'd be interested in wanting to find every part across these 3 interviews where they discuss data sets and how data comes into play with some of these machine learning concepts. The issue, however, is that this is about half an hour, and then the other 2 are 41 and 47 minutes respectively. Now, while I could sit here and listen through all of these, or listen through them on 2 or 3 times speed and try and skip through, it would probably be easier to just let a language model program like NeedleInAVidStack handle this for us. So after cloning down the repo, what we're going to do is use UV as our package manager here, and we can use UV sync to first make sure that all of our packages are in order, and then do UV run source app.py. As mentioned, NeedleInAVidStack is a very lightweight and simple Streamlit app that's meant to just be a quick front end for running this analysis. At the top here, we have our prompt that we can use. And more specifically, I have this set up as a template so that you can replace things like target topic with what you're looking for. So mine's going to be analyze this audio for specific examples of data sets. And then these are instances where they discuss how data sets come into play with machine learning and AI. And then a few things down here. I can say data sets, what specific aspect. And this prompt is really tuned to make sure that the language model is going to really consider the specifics of what you're asking for. So it'll look for and put out the timestamps of when it was mentioned and a little bit as to why it thinks that this example is relevant to your ask of looking for things like data sets. And then it has some other additional instructions, like don't include general discussions without specific examples, and say how kind of confident you are. I found that this prompt that I came up with was very effective at making sure that the language model didn't try too hard to make up scenarios that didn't actually exist within the videos. As we'll be using the Gemini models and their wonderful auditory examples here, we can use either the Gemini Developer API or the Vertex Model Garden connection through something like GCP. The easiest for the average consumer is likely going to be the Gemini API. We'll be running this through the recently released Gemini 2.0 Flash, and what we can do is just paste in our API key here real quick. What we also do is want to create a folder and hold all of our videos, so I've gone ahead and downloaded all 3 of those interviews as MP4 files and put them in my videos folder here, which brings us to discuss a little bit more of how this pipeline works. Essentially, while we're processing videos here, much of what I've found is that it takes a lot of time, effort, and money to directly process the videos and its visual content. But if you're more concerned with things that have a lot of speech, which most of the videos that I work with have, what we can do is more focus on the audio files. So what NeedleInAVidStack does is it takes your folder of videos, converts them into audio files, and then runs that through the prompt that we just defined to extract out all of the insights and timestamps and descriptions for whatever content we're trying to discover. So the first step here, after pathing over to our video folder, is converting them to audio. As such, one of the dependencies of NeedleInAVidStack is going to be having FFmpeg installed on your machine. And after a short wait here, we can see that all of these video files have been converted into audio file MP3s. So now we're ready to kick off the analysis. So after clicking this button, we can see that that will start, and I will let it run for a few minutes and see what the output is. And shortly after, we can see that our audio files have been analyzed and our analysis is complete. Now I have it show the raw text as well as save all of the raw text and text files, but we can render it nicely in Markdown here. And then we can see in this rendered analysis how powerful this tool actually is. We can see at these specific timestamps exactly what's being discussed and the context for it. So we can see more specifically in something like this AI and robotics video that at the timestamp of 1353, they discuss needing a Wikipedia for robot motor control or needing a large data source with diverse information to apply for this machine learning process, with a direct quote like there isn't data lying on the internet of how exactly to move a robot's fingers to tie a shoe, for example. And then we can see that around this timestamp, Andrew Ng and Chelsea Finn are having this conversation about data
on a very
here.
small amount of data. That won't work very well. You need large amounts of data in order to learn something.
So we can see that it was actually able to work, and we can of course go back and verify. However, it's a lot easier to verify these individual timestamps and also vet them out based on the analysis from the language model rather than doing this all manually. So with that, we can see the value that something like NeedleInAVidStack can provide if you need to do this automated content extraction across vast video libraries. So with our second project demonstration out of the way, let's take a look at the third and final project, QuicKB. The whole idea around QuicKB is inspired by some of the work that I've done with fine-tuning embedding models, essentially those models that are used to convert the different chunks that you make from documents, put them into a vector database, and then be able to retrieve for retrieval augmented generation. The embedding model that's able to convert that text into a vector representation that's used to do the similarity calculations for retrieval is what we're kind of focusing on here, but combining it all together to create an optimized knowledge base. What I mean by that is essentially QuicKB is going to take in all of your documents, your unstructured information as text, and then fully chunk it and create a personalized embedding model fine-tuned on your chunk data for an end-to-end knowledge base. So you'll have all of your information out in nice chunks, as well as that tuned embedding model to improve the retrieval performance. For this one, it would definitely be a little easier to look at the high-level diagram of how this pipeline actually works before demonstrating it. Essentially, as I said, you're going to take your domain-specific text documents as an input. Those text documents are going to first go through the step of chunking. All of the chunkers that I've implemented into QuicKB come from the wonderful work from the Chroma research team on evaluating chunking strategies for retrieval. I have a couple videos going over the entirety of this report and applying it ourselves, so I'm not going to tell you the specifics of how each one of these chunkers actually works. I'll leave that video to pop up right now so you can check it out, or in the comments below for further information. But after using the latest state-of-the-art chunking techniques on your text documents, essentially what we're going to be doing is preparing the embedding model. While you can use a basic or base embedding model, something like OpenAI's or AllManyLML6 v2, what I found is that especially once we start to get very niche into our topics and our domain data, the generalization of embedding models tends to be a little bit lackluster. Essentially, they're made for every single use case, not necessarily your domain-specific use case. So using the text chunks, what we're able to do is actually create a synthetic Q&A dataset using language models once again, taking each one of these chunks and generating a set of questions that corresponds to that chunk. Essentially, these questions are meant to represent things that your users would be saying in something like a RAG app, and identifying the golden chunk that would need to be retrieved to best answer that question. We can automate this process a little bit using language models, of course, to create this synthetic Q&A dataset and augment it to a size that actually matters when training embedding models, and then take one of the latest open source embedding models, train it on this, and package it up back with our text chunks. So at the end, you will have your optimized knowledge base that is ready to be put into your specific vector database. All of the chunks plus an embedding model that can best represent all of those chunks and generalize towards unseen queries to better pull the correct information that would be needed at runtime for your RAG-based application. So naturally, this project is a little bit more involved and in the realm of, machine learning pipelines, more so than our NeedleInAVidStack or PowerPoint 2 description applications that we just shown, but it can be equally as powerful if used correctly. As mentioned, you can independently do the document chunking, training data generation, as well as embedding model fine-tuning using this tool. You don't have to do all of them at once, although you can actually do all of them at once, which we're about to demonstrate. So after cloning down the repo and installing the requirements, what I've done is set up an environment here that is actually backed by a GPU. So right here, we are running on an A40 with about 46 gigabytes of memory. You don't necessarily need 46 gig of VRAM to run stuff like this, but I would recommend having about 24 on average to be able to efficiently and quickly create these optimized knowledge bases. Now, all of the configuration of QuicKB is done in one single YAML file, which makes it quite long, but I've segmented it out and clearly put some comments here so that you can see a little bit of my thought process between configuring this setup. At the top, we have our pipeline control. So there's three options. There's chunk, generate, and train, and you can do from stage to stage. From chunk to train is the full pipeline, but you could do from chunk to just do the chunking, or from chunk to generate to just do the chunking and generating the synthetic data Q&A. Whatever stage of the pipeline you want to do, you can control it with this. There is also a couple global settings. So we have our path to our knowledge base, which is going to be where we are containing our source documents that we want to create the knowledge base from. In our case, what I have here are 4 different text files, and these are all going to be court opinions. These are nice, long, lengthy, specialized files as it's all legal oriented, and these all kind of relate some way to artificial intelligence. But these 4 files are going to represent the ones that I want to chunk and embed into my vector database and create the specialized embedding retrieval model for. So I will path over to my knowledge base, which I have under a folder called knowledge base here. I am also going to pass in my Hugging Face username and Hugging Face token. This is going to be for the integration that I've put here with Hugging Face. At each stage of the pipeline, you can actually go in and have it automatically upload to your Hugging Face account. So you can have the knowledge base, the Q&A data set, as well as the final model actually be put onto your account. And you can also use Hugging Face datasets and models and pull them back into QuicKB to do the different phases of the pipeline. Then the first pipeline stage config is going to be the chunker config. We can path to an output of where we want our chunked knowledge base JSON file to be output to, which I just have it as an output folder. And then we have our chunker config. As mentioned, I'm not going to go over every single specific chunker in this video, as I already did that in one of the prior that I'll have linked below, but all of the ones that I have installed are a fixed token chunker, a cluster semantic chunker, a LLM semantic chunker, Camrat's modified semantic chunker, and you can configure these in multiple different ways to do either token-based, character-based, length-based, recursive-based, different chunking setups. In mine, all I'm doing is using the recursive token chunker with a chunk size of 400 characters with these separators to create my chunks. I also have it with a Hugging Face hub upload config, and I want it to push to the hub in a public repo in this dataset ID. So this section of the YAML file will fully handle the chunking of your text documents, and I'll put it all nicely into a JSON file and upload it to Hugging Face if you want that. Moving on, I then have the question generation config set up here. We can then again have our output path. This is going to be our training data for our embedding model. So I have it output to train data. And then what we have is a light LLM config. What light LLM does is it provides a unified framework for actually accessing language models so that you don't have to deal with all of the different API specs or connections to. You can just make your code all use just light LLM's proxy and run through any sort of language model through it. So this lets you specify both the embedding model that you want to use as well as the language model that you want to use, depending on which one it is you want to use or care to use, or which ones you might have funding for or access to. As a plus, you can also use local models if you're using something like Ollama or VLLM with an endpoint that is part of the OpenAI API spec. I have additional examples in my README here, of course, for how to set up the different configurations to do this kind of thing. But for me, from all of my chunks generating the Q&A training data, I'm just going to use GPT-4o Mini since we'll be generating a couple thousand questions, and this is a cost-effective example, so that's what I'll be using. I also want to use text embedding 3 large. The reason that we're using an embedding model right now is because we're going to be using some different deduplication efforts. Pretty much going to be looking at all of the questions that we generate, putting them through a similarity comparison, and if they don't meet some sort of threshold, removing them because these questions are too similar. We want unique questions for each chunk so that our training ends up actually being able to generalize towards unseen questions better. As we'll be doing a lot of calls, I have some parallel processing arguments here, so you can define the amount of concurrent parallel workers that you want to be able to ping your API here. For something like OpenAI's API, my account is a couple tiers higher than the average, so I can actually hit it with a lot of requests all at once. So I have 150 workers working with no call limit at all, but you can set this up to have some form of rate limiting and limited amount of workers if you don't have those different levels or are using something like a local model and don't have a lot of processing available. And then of course, I will be uploading this to the hub. So with this question generation and training data config out of the way, we can take a look at the final step, the model training configuration. As a note, much of what this model training configuration goes over is also something I covered in a prior video for fine-tuning embedding models for retrieval on domain-specific data, so I'll gloss over a few of the specifics here, but of course I'll leave that video linked in the description below for you to check out the fine details. But with that being said, the model ID that I'm going to be using comes directly from Hugging Face. It is going to be ModernBERT Embed Base, which is a phenomenal base embedding model at only 149 million parameters, so pretty easy to train. We'll be employing Matryoshka dimension representation learning, a technique that I cover in my other video for training this as well, so we can define what sort of different truncated dimensions we want to be able to train at. More specifically, I have a train dataset config. I set this to local as we'll be running the full pipeline and can use our outputs that are going to be in our output folder here. But if you are picking this pipeline back up at the end here, you could also download these from the hub. I have this commented out, but you can pass in a Hugging Face ID to download and use there. We then have a bunch of training hyperparameters. We're going to be using the sentence transformers library and some of their sentence transformers trainers in the main training script that happens here. So this code is not the most approachable if you're not very into the language model training community, but I have some recommended training hyperparameters already laid out. The biggest one that you should care about, though, is that our output path is also going to put our model into the output folder here, and we'll be uploading that to Hugging Face as well. If you're more familiar with the training process of things like language models and embedding models, you can mess around with some of these hyperparameters and see what might work to push the performance even further for your specific use case. That brings us to the end of the configuration file, which means that we should run the pipeline and show how it performs. So with this simple Python source main.py, we shall kick it off. We can see immediately that our recursive token chunker has been ran over all 4 of our text files, creating 429 tokens in total, and it's already gone ahead and uploaded everything to Hugging Face. So now it's going to be running the generate stage of our pipeline, and in just a few seconds, we're going to see all of those workers and their API calls start to come back to us with these generated questions. And just like that, we see our generated questions spilling in. Looks like my camera's covering it a little bit, but it's taken just under a minute and a half to generate all 429 questions. At this point, it is going to process all of the embedding vectors for these questions so that it can run the similarity calculations across all of them to deduplicate our questions. So after generating 16 questions, we remove a bunch and get a clean 1600 training records. That is where we are now able to go to the train stage, where we've already processed all of the unique chunks in our knowledge base and validated that everything is in a good format and downloaded the modern BERT model. So with everything downloading and our data consistency validation passed, it is going to kick off the actual training part. So we can see our before training baseline results table here pop up, and we're seeing our normalized discounted cumulative gains at a K of 10 for something like 768 dimensions be about 57%. So keep that in mind as we run through our training and get to the optimized version. And so after all of about 50 seconds of training on these examples, we get our post fine-tuned results here. So we can see that we went from 57% to 67% on this specific metric. So cool to see a 10 percentage point increase. And what it's doing is already starting to upload our model to Hugging Face, which is shown right there. And so in no more than all of about, less than 5 minutes, we have our full output, which includes a knowledge base of all of the chunks of text that we have, where they come from, and a unique identifier, our training data, which is going to be a anchor, a positive, and the question and chunk IDs here, and all of the questions generated for each one of these chunks, as well as an embedding model that's been fine-tuned on all of this data here. You can see in this metrics comparison file that I spit out at the end that we've gotten some decent gains across all of the different dimensions for our embedding model, with percentage changes of 17% for the specific metric that we were considering earlier, and some of these having even more gains, like 42% on the accuracy at 1 at a dimension of 128 when truncated. These have all then been uploaded to Hugging Face automatically, so I can see my modern BERT embed QuickB for the video here, as well as the Q&A dataset and the knowledge base here. which allows us then to do something like load up ChromaDB, download our model, create something like a custom embedding function that will go through our model, and then within our collection, embed everything that we've got from our data set in Hugging Face into that database collection, and then be able to query our results that have all been nicely chunked for us with our custom specific embedding model, doing all of the embedding of these chunks into our vector database and all of the representations of our queries for the semantic similarity retrieval at runtime. Using the techniques that I employ in QuicKB, I've been able to improve my RAG retrieval performance on some of my pipelines by up to 60% of an increase. So some real big gains to be made with optimized chunking and embedding model fine-tuning. That being said, this project is a little bit more of an involved one. However, if you are the person who's setting up retrieval augmented generation applications, which are some of the most popular formats right now with some form of retrieval, something like this could help push your performance from just basic and general to specialized and well-performing. One of the things that I think is really important is actually the retrieval step in retrieval augmented generation, hence why I put this entire project together. My main hypothesis around this is because it doesn't really matter what language model you have if you're trying to synthesize and retrieve specific knowledge, if you're not actually doing that retrieval step right. The best language model cannot interpret and contextualize bad retrieved information if it's not relevant to your user's queries. So working to really optimize the accuracy, efficiency, and performance of the retrieval step so that it better represents what questions and what information we're trying to retrieve at runtime can really push the performance and user satisfaction of a retrieval augmented generation based application. But with the third and final demonstration out of the way, this concludes the showcase of the 3 AI projects that I've put together to make my life a little bit easier. What I hope I've been able to demonstrate through the course of this video and these 3 demonstrations are really 3 practical applications of different machine learning or artificial intelligence based systems. I think that with a lot of the proliferation of artificial intelligence based applications that I've seen, a lot of them aren't necessarily the most specific to AI or necessarily even needed AI in the first place. However, I believe that these 3 examples are 3 that can clearly showcase the power of some of the cutting-edge technology baked within embedding language models or different machine learning systems. And while I'm at it, these have all helped me solve some problems that have come up in my life and in things that I've wanted to do. So maybe one of these solutions is something that you're actually able to use as well. So if you enjoyed learning about a few of the applications and projects that I've put together and applied AI to myself, I implore you to check out the links in the description below, give the GitHub repos a few stars. And if you liked the video, consider liking the video. If you have any questions about anything that I went over, leave it in the comments below. And if you want to see more and support the channel, consider subscribing or dropping a membership. But with all that out of the way, thank you for watching, and I hope you have a great rest of your day. Thank you.